Hi there. Today I'm having a look at an HP3580A audio spectrum analyzer that I bought quite a few years ago now and started to repair the unit, but then due to time pressures had to shelve it, and it's only now with coronavirus giving us a little bit of extra home time that I thought I might drag this out and have a look. When I'd first got it, the unit didn't power up properly and things had been damaged. Some of the caps on the control knobs are missing. There's a little bit of cosmetic damage, and someone previously had removed the power input module, which has the voltage selector and fuse in it, as well as the line input connector. Anyway, I had done some work on the unit and got to the point where I'd found that the plus and minus 11.5 volt supply inline fuse on the power supply regulator board, and that was blown. So after repairing that, I got to a point where I ran out of time looking at it. So today I've pulled this out and just double checked all of the voltages again without the frequency module in place, and it's working fine as from what I can see so far, and just starting to make a few notes because my memory is getting a bit shaky on this, and I can't remember precisely what I did, but it's obvious that I've repaired the fuse and got the power supply working again, but I've got some red stickers on the frequency display module to indicate that there's attention needed there. And after checking the voltages and firing the unit up without the module in place, we're getting something on the display. I'll just let the tube warm up, and you can see that there's some rubbish coming up on the display. But if we clear the write mode in the memory of the unit, we get a horizontal line at the bottom of the display, which is what we would expect. So I'm guessing, without too much evidence, but guessing that there's probably not a lot wrong with the unit apart from the frequency display module. I have another one of these units that's got the mechanical frequency adjustment rather than an electronic frequency adjustment and display, and that too of recent times has stopped sweeping, so I've got to have a look at that as well. But this unit looks to be at least doing some of the things we expect. I've ordered and found on eBay an input module to replace the missing one that should be on this unit, and so we're waiting for parts there. I've also, because I've had experience in the past with these MOSTEC devices that are used for the frequency counter display, I've had on other different equipment this particular part, the MK50399N, I've had failures of that part in the past. It's a PMOS device, and so as a precaution I've also ordered a replacement chip for that. I'm guessing that's what's causing the fault, but I may be wrong. This is where we measure the power supply volts on the HP3580A, and we can check positive volts, positive regulated 10 volts, which is good. Negative regulated 10 volts, which is also good, and the 150 to 158 volts, and this drives the DC-DC converter for the accelerating voltage in the CRT, and you can see it's 154.8, which is also in spec. The 10 volt supplies are 10 volt supplies are supposed to be within plus or minus 50 millivolts, and this is certainly the case for this. There's also another test which tests the ripple voltage, and that's got to be better than 0.1 millivolts AC. With the AC range zeroed out, with the meter probe shorted, then we connect to the positive regulated supply. We're getting worst case about 0.02 odd millivolts on the negative supply and 0.03 millivolts on the positive supply ripple, and the spec is it's got to be less than 0.1 millivolts, so the ripple on that supply is also in spec. I decided to power up the digital display just to determine whether or not it was faulty, and after a few tests just to check that the circuitry wasn't shorted or whatever, I powered the unit up, just this board here, and you can see, if I zoom in, we're getting the digits coming up. Interestingly, one segment's gone here, second from the left, and that's probably because the gold bomb wires to the actual LEDs may be damaged. Now, what I noticed first up was that I had blurry digits in some places, and so I thought, oh, I better just take this out and have a look. Well, these are the old type magnified LEDs, 7-segment LEDs that HP used to produce, and just zooming out, here is the magnifier. You can see that it's in pretty poor condition. It's cracked, it's had bits broken off of it. Looks like it was probably the one that was in this unit originally was pulled out, and the unit was used as a donor for another unit. So anyway, after having a bit of a look around on eBay, I can't find anything that's suitable, and as you can imagine, this is 50 years old. This particular unit's about 40 years old, but it's a replacement part that's probably unobtainium. I have seen examples that people have in various YouTube videos, but the likelihood of actually getting one that's right for this is probably pretty slim. So having a look on DigiKey, I found some suitable surface mount 7-segment LEDs that if another circuit board was made up, we could actually replace the original display with that new board, and may make for a better display. At least we won't need the magnifier with the newer devices being used. This is the A2 circuit board out of the HP3580A audio spectrum analyzer, and one of the minor faults that was occurring was that the tracking generator output from the unit was not giving any sensible signals, and after considerable testing just to try and rule everything else out, it's come down to basically this guy here, U7, which is an MC 1496G double balanced modulator demodulator. I didn't want to be pulling any ICs out unless I was fairly sure that there was no other cause for the fault, and we've been right around the circuit, supply voltages, signals going into the IC and no signal out, but I didn't want to just leave it at that. These devices can be very touchy on biasing, not only the actual bias pin on the thing, but also biasing on both sets of inputs, and have checked every DC level going into the chip to make sure that the biasing level is not too far off, and then even to the point of setting the balance control here. I've marked that balance control before I adjusted it, and then I've adjusted it through its full range, and we've still got no output. So I'm fairly confident that, without pulling this device out yet, that it is the culprit. So I've got a couple coming off of eBay, and hopefully in a week or two I should see them, and I can then at least swap out this one and see if I'm right on this particular issue. So anyway, the next step after I get all these parts in is to get at least this part of the unit working, having calibrated frequency display working on it, and then I can start doing the rest of the troubleshooting so that I can progress through the system and get it fully operational again. Today, some mixer chips turned up to replace this chip here. The original was an MC1496 balanced mixer, and I actually managed to get 1596 simply because these 1596 mixers were cheaper than the 1496, which seems quite silly because the 1596 is just the extended temperature range version of the 1496. Anyway, I'm going to put one of those in to replace the existing device, and that should fix our tracking generator problem, because we're not getting any signal out of the tracking generator, and it was traced to the output of this chip here in the A2 board. After installing the new chip, replacing the old U7, we've now got quite a decent output on the tracking generator, so that's at least resolved one of the issues in this device. As the original frequency display card had been damaged, I thought before we get on to building a new replacement board, I'd make up a quick board with the display so that I can further troubleshoot issues relating to the frequency display. And as you can see, the second digit from the right, which is designated as digit 2, is all segments are on, and it's brighter than the rest. And in fact, if I change the frequency value, you don't get any change in digit 2. And this is because the cathode drive, the digit select if you like, is permanently on. And with a bit of probing, basically what the circuit is a ULN 2004 open collector Darlington transistor drive array that is used to drive the digit selects, or essentially the common cathode of each display. And following that back through, we find that the driver MOSTEC MK50399 drive or counter is faulty on that pin, and in fact the digital signals we're getting are all high, except for when it should be going low, it's only going down 400 millivolts. Fortunately, I've already ordered one of these MOSTEC devices because I have had experience of them in the past and that of them failing. So the next step is to receive that part and replace it, and hopefully we'll get the frequency display fully operational, and then I can send off the artworks for the boards to be processed so that I can make up a new display which will have slightly bigger digits than the original display, but fortunately will fit within the window here on the frequency display. So apart from the digits actually being bigger, there should be no difference to that display. So that's the progress so far. While gathering all the necessary information to start making a new PCB artwork for the 7-segment LED display on this unit, I noticed that the pin numbering didn't match up at all with the display. You can see the numbering on the actual display there goes up to 16. There's only 15 pins on the actual mating circuit board, so I don't know what these numbers relate to, whether there was a different display at some point. Certainly I've looked through the most recent and older versions of the manual that I can, including looking at backdating sections of the manual, and there's no reference at all in the manual for anything other than this version of the 7-segment display. So I was at a bit of a loss as to why this is in the manual, but it is what it is. And so instead what I did was just buzzed out the connections on the actual circuit board, on the A33 board, which contains all of the ICs that drive the 7-segment display, and just mated everything up to make sure that it would operate. And I did that with the temporary board that I made so that I can continue on troubleshooting before I complete the final replacement. So this then leads on to my design of the actual replacement board. So here is the schematic of the new 7-segment LED displays. It's using a Kingbright KCSC02-105 7-segment display, and these devices are available, I think, from pretty well most of the usual suspects, such as DigiKey, Mauser, RS and Element 14, so they're not too hard to obtain. And over on the right hand side we've got the header strip plugs into main A33 board. Then going to the PCB layout itself, I've got all of the dimensions that we had measured from the window and the original board, so that we'll try to keep everything in line with the original PCB that the LEDs were mounted on. And while it's not the best practice, some of the pads here, the surface mount pads, have vias through them, but in this case, as I've only just hand soldered the 7-segment LEDs onto the board, it's not as much of an issue as if you were stenciling solder paste onto the board. So that's the artwork for the new display that I sent off. And next we'll see the result that was returned. Here's a populated frequency display board, and all I've got to do now is put the right angle header onto it, and it should be ready to fit in and fully test in the unit. I've done a quick digit segment test on all the digits, and they're all working, so that's a good start. And the next step will actually be to try it in the equipment. Here the new display board has the pin header on it, and we used the pin header from the old board sitting off to the right, and it's now pretty much ready to go. Right, now the new display is plugged in, and we can see that apart from the second last digit on the right, everything is working, and that's just because the counter chip currently is permanently selecting that digit rather than multiplexing correctly. So we have to account for that, but that doesn't look too bad, and it all sort of fits within the display area. The digits are bigger than the original, but the original did have magnification to bring the size up, and also currently it's a little bit skewed in there because the final alignment of the board hasn't been completed. We've just got that in temporarily. So the next step is to get when I get the new MOSTEC counter, then and replace the existing one, will then have the display fully functional. Just to give a bit of an overview of the spectrum analyzer, it's a fairly traditional design where you've got the input section with attenuators, and then you come up and you've got a mixer, and from circuitry down below there's a local oscillator input into that mixer as well to give you an IF output frequency of 100 kilohertz, and then we've got the IF stage there, and then it goes through a little bit of amplification, either linear or log depending on what's selected, with a detector. And it comes over here and we've got a video filter and video amplifier, and then before it gets to the CRT it comes into a digital storage board which allows sweep samples to be stored for display, and we can have either live or stored data displayed. So we're digitizing the signal coming in, goes into some memory, and then there's a D to A pair of D to A converters on the output that drive the X and Y of the CRT. The rest of the circuitry is basically related to the frequency and sweep setup, and most of this is related to the front panel controls. There's a local oscillator in here, and off of that there is the tracking generator output and amplifier. So that's basically just a quick rough overview of the system. Oh yes, there's also, if we go over here, the actual frequency display board in the bottom right hand corner. So that's essentially it. Fairly simple design, and something that you probably wouldn't design these days for such low frequencies. You'd just use a discrete Fourier transform to generate the frequency domain display. While evaluating my HP3580A for various issues that it has, I had noticed that the sweep was doing an odd thing. We were actually sweeping from right to left, but there were sections of the sweep that was sweeping from left to right, and this seemed pretty odd. And anyway, I've now just set up a large enough peak to actually show that a whole peak over a number of sections of the sweep. And as you can see, there are individual sections that basically appear mirror image, and simply because we're sweeping from right to left rather than left to right. I suspect that the digital board has had a bit flipped in some way, or there is some the counting scheme is running in reverse, and this is separate to the actual sweeping that the system has, because the sweep input comes in, which is also digitized, and then the whole output is then turned back into an analog signal to display on the CRT. So it's obvious that there's a bug in the digital board, which is this top board up here. It's obviously each chunk of the data is being correctly digitized, but then it's being reconstructed in the wrong order, in reverse order, causing this weird pattern, which would normally be just a peak such as that. So this at least gives me a bit of handle on what I'm looking for. So I've been able to narrow down the issues with both of these units by swapping over the digital boards between the two, and the issue of lack of sweep on the unit that is pictured at the moment has now changed to the issue that I described previously, and similarly the digital board placed in the other unit now gives the same symptom that was in this unit being basically no signal, or a very small signal, a little bit of noise on the baseline and nothing else. So I can be pretty confident that in both cases the digital boards in these units are the cause certainly of the sweeping issues that we have. So now what I'm going to do is start working on this unit with the original digital board back in it and actually trace out the signal and see how far we get with that, because this might be a simpler issue to fix, and the idea being that we get one board working, and once that's working then we can use that as a comparison for the other one on some of the digital signals, so we can get an idea of what is occurring in that board. This is the detailed circuit schematic of the Amplitude A to D converter in the spectrum analyzer. This takes the video in from the previous processing and converts the analog video signal to an 8-bit digital signal. As you can see here, it's a fairly simple counting type A to D converter. We have a comparator here, goes into a latch. We have a peak detection circuit here that will flip the counting direction of the two counters here, two 8-bit counters, so it will hunt up and down to line up output data to the input data. What we've seen is that there is very little activity on the data lines here, and what I'm going to do is set up the MSO so that it's looking at the output data lines and the input video signal, and we can then look to see what sort of activity is occurring on those data lines at the point in time where we've actually got a valid video signal coming in. Here are the probes from the MSO set up to look at the data lines coming out of the Y-axis A to D converter. Now with the system running, you can already see that there's only activity on the top trace, which is bit 0, and if I now connect up the sweep signal, if I can get my probe on there, you can see that just get that to having trouble probing here. There we go. And you can see that a peak, and I've got an input signal on there, that the data bits for the peak, or in the sweep, the section of sweep where the screen's active, we're getting data bit activity, but only on bit 0, and it's 0 down through to 7, or as in this unit they've classed it 1 through to 8. But you can see that there is 0 activity past bit 1, and as there's little else apart from some multiplexes on these output lines and the D to A converter, which is basically a direct ladder network, or with some buffering on some of the bits, that it's pretty obvious that the first counter, the low order, the lowest significant nibble of the counter, is just not counting past the first bit, and so I'm suspecting that that counter chip has failed for some reason, and we just need to replace that. U5, the top of the two counters shown in the schematic here, is the one that's suspect, and we're going to rip out. This is an MC14516 binary counter, and it looks like there's an internal fault, because obviously there's no rippling effect of the counting past the first bit. So we'll take that out and put a new device in and see how we go. Well, I've just replaced the counter for the low order nibble of the A to D converter for the Y-axis, and it looks as though everything's working fine now. So it does need a bit of adjustment. The baseline has to be centered on the bottom line of the graticule, and the frequency adjustments need to be tweaked, I think. But essentially it looks like this unit's working again. We've still got the other spectrum analyzer to do repairs on, but at least now I've got a fully operational unit. Particularly on the digital board, I can use the digital board in the working unit, use the signals in that as comparison with the digital board in the still faulty unit, and to give me a guide where I haven't got signals shown in the manual. So that's a good result so far. Back onto the digital board that is giving the odd sweeping. I thought, right, the first thing I'll do is, seeing it's a sweep related thing, I'll look at the horizontal sync pulse that comes out of here, out of this gate U23C, and when comparing the working unit with the faulty unit, the horizontal sync pulse in the faulty unit looked rather odd. As we can see here, one of the inputs comes directly from a clock, which is the clock for both of these counter chips, and the other input to the gate comes out of the carry of the most significant nibble. Now, what we've already seen on screen, we're getting a small chunk of sweeping in the correct direction, being from left to right, and the overall sweep is sweeping in the wrong direction from right to left. And that tends to me to indicate that there's something wrong with particularly the upper or most significant nibble of the count. So alright, I thought I'll go and check the up-down select pins on the counters, and unfortunately in the schematic here we don't have any indication. These multiple pin indications here and here, they don't show the up-down count. So I went back to the board and just quickly buzzed out the connections for the up-down counts, and both counters are connected high, which is the logic level required for both counters to count up. So without much more evidence than that, it's obvious that U57 here is counting in the opposite direction. So I just assumed that that counter, for whatever reason, has failed internally, and interestingly it's the same type of device was used in the other A to D converter that had also failed. So anyway, that chip is to be replaced. Well, success. I've just replaced this counter chip in here, U57, and we have now got the horizontal scan running from left to right rather than right to left as it was. Today I've just received the input module, mains input module for my HP3580A, and there's quite a few connections on it that we've got to line up with the instrument, but two connections that can be done straight away with just some soldering. These R and S, and it needs to have a link going across here to bring the line in through the fuse out to connection H, and similarly from the neutral in, connecting this across to from P to N, and the holes are already in, respective holes are in the board, and it's just a matter of putting some wire in. And for Australian standard, I'm looping this across with a brown link and this across with a blue link to match up with standard colours used here. Okay, the links are now installed, and I found a little bit of surface corrosion on some of the connectors on the other side, but a bit of deoxit, and we've cleaned that away, so there shouldn't be too much of an issue with this input module. Just going through the relatively simple exercise of reconnecting the mains input module. All the wires had been chopped when someone had obviously cannibalised the unit for the input module, and doing the re-termination, I thought, oh, I may have to buzz out the transformer or do some tests with the transformer disconnected so that I make sure that everything's correct. However, I do like HP manuals. They're not absolutely perfect. In the time I've found a number of errors in manuals, but they're generally minor. Usually the manual, certainly from the equipment from the 90s going back, are very comprehensive, and initially I thought, oh, I don't have the wire colours, but I did a quick check in the manual and I noticed that there's this numbering here, and you can see it's got a what looks like a angle bracket on its side with the number in the bracket, and the manual gives you an indication that the wire colours use numbering the same as the resistor colour code. So for instance, this one here is black being 0 with a white stripe being 9, and this is done for all the wiring. So even if some of the wiring has aged a bit and there's been a bit of colour bleeding and it's not necessarily 100% clear from wire to wire whether you've got the right colour. Two different units here are showing, one looks like a purple background and a green stripe, and the other one looks like a black background and a green stripe, and in fact it is black with a green stripe, but the purple looks very faint, and it really will depend on the lighting used and whatever when you're looking at it. So these numbers give me the wire colour codes, so it's a relatively easy exercise without having to rewire this, without having to go through the additional checks of making sure that the transformer windings are correct. I will still, though, before powering the unit up with the new input module in place, disconnect the secondary transformer and just do some tests with a variac to check that the secondary output voltage does line up with various input voltage selections. But it's just one of those nice things about these old comprehensive manuals that companies like Hewlett-Packard made. It just does make it a lot easier. They've thought of everything. I've taken off the rear panel of the spectrum analyzer to give me a bit easier access to get into the transformer, work out whether the wires need lengthening when I put on the crimp sockets to connect to the input module. Anyway, in taking the back panel off, I found that some of the wires were a bit short over here and have come off of the output level adjustment for the tracking generator, and I'm also pretty sure that that panel has been off one or more times before because these wires just broke fairly easily. Now I do know that this type of wire wasn't designed to be super flexible and consequently does fatigue fairly quickly when bent, but some of these, they were only holding on by one or two strands, so the strands have been broken in the past. So anyway, that's a little bit of an extra repair exercise I've got to go through, lengthening some of these wires and just making sure the connections are all okay. But I just thought I'd let you see the back end and all of the wires here coming out of the transformer that need crimp socket pins on them with heat shrink so that they can connect into the input module. Just received the D-sub socket pins, crimp socket pins, and they look to fit just fine. They've got a moderate amount of holding force, so the sockets are not going to shake loose from the header pin, As you can see on A, I've not fully pushed down the socket pin. That was just to see what it looked like standing off, and then on B we've got one fully pushed down. It's reasonably firm on that pin, so that looks quite reasonable. They're rated at about an amp, and I think the circuitry should be drawing far less than that, so we won't have any trouble there, I don't think, as far as any heating due to excess current. So the next stage is to see how long the existing wires are and whether we can just crimp them back on these and have enough length to fit the mains input module correctly back into the rear panel. And as you can see, I've also labelled all of the sockets with the actual letter that appears on the input module, so that we don't have to just rely on the wire colours. So that's an extra way of verifying the connections are correct. Here's a quick test setup just to double check that we can select all the mains input voltages correctly. And currently I've got the unit plugged into my Variac, and we're set at 240 volts AC, and on the display we've got 37.4345 approximately volts AC across the series connected secondary windings on the transformer. And just to put a little bit of load on it, I've got just a 10k resistor across those. But basically, when running all the different mains voltages, I'm getting a range from about 37-38 volts mostly, and for a 100 volt input it does go up to about 40.2 volts. So all of the voltage selections seem to be pretty right for the unit. So now we can go ahead and start doing something about reassembling the whole back panel. We can then just fire it up normally with a standard IEC mains lead. Hi, well today I've finally received the counter that I need to fix the frequency module from this HP3580A. This has been a bit of a saga, and it's yeah, to say it's a saga is probably a bit of an understatement. I purchased this back in, I don't know, early April, and what with COVID-19 and all of that, I've been expecting that all of the parts that I've been getting in for these units would take some time. Well, this chip took quite a bit longer than I expected, and what happened was I was able to track it via the eBay tracking, and it got here to Australia on the 8th of May 2020. It is now the, according to my watch, the 9th of June 2020, and I followed up with DHL a few days ago, maybe about 3 days ago now I think it was, and gave them the tracking number, and they said, oh, let us check, we have to check with Australian Customs. And they came back with the story that, oh, Australian Customs have rejected the package and it's on its way back to China. Great. So I did two things. I found another chip online, which actually was slightly cheaper, and I sent a request for refund via eBay. Well, guess what? Today it turned up. So DHL didn't tell me what was going on, and so I've just now had to close off the refund request with eBay, and sent a short message to the seller to let them know that everything's okay and I've received the goods now. But yeah, it's been a bit of a saga, to say the least. So Next step is to take this chip out of here. I'll do it the safest way I can, which is to actually just chop all the legs so that I'm not trying to overheat the board in any way, even though it's only a double-sided board. And then I'll desolder each pin individually, and then use my desoldering station to actually clean out the pads, and we'll get the new one installed and see how that goes. But hopefully we should then, if everything works all right, we should then be ready to actually start recalibrating both units. So that's it for now. Just removed the frequency counter chip, and I've still got to use my desoldering station to clean the holes. But out of interest, just as I was looking in more detail here, you notice daggy soldering on this pot that sets the frequency. That's, to me, another bit of evidence to show that possibly this whole circuit board was just replaced, and again the unit was used as a parts donor. Now the Mostec MK50399N counter chip has been replaced in the frequency display of this HP3580. You can see that we've now got the display working beautifully, and the fault with the fourth digit's now been resolved. So both these spectrum analyzers are now ready to be fully recalibrated, and I shall go through the procedure straight out of the manual for that, and we should have two fully operational devices.